Uh, yeah, good morning, actually. Thank you, Nargis, for introductions and also give opportunity to talk in a SAAO Colloquium. So today I will talk about like multi-wavelength approach of AGN feedback at low redshift, starting from high mass galaxy clusters down to the galaxy groups and even at individual uh, elliptical galaxies. So this is I will cover in this talk. I will cover is like one slide of introduction and motivation, and like two types of agent feedback, and some examples of radio mode agent feedback, and some I will give some little bit perspective on high redshift studies of agent feedback, and finally I will tell about this multi-phase uh, view of agent feedback. So I will start with the introduction slide as usual. So if you see the galaxy cluster in an optical, it looks very red and dead. And we can see that centrally one galaxy called as a BCG or central dominant galaxy sitting at the gravitation potential, deep gravitation potential, and it looks very red and dead, and it's a little star formation is there. And if you look the same cluster in an X-ray with the same field of view, then you will see the hot X-ray emitting gas through the Brahmström radiation, and the hot diffuse gas with a temperature of 10 to the power 8 Kelvin, uh, and it's that hot diffuse gas called as a intercluster medium, and that intercluster medium, it like most of the barons, like 90% of the barons are mostly in the intercluster medium. That makes the cluster through X-ray is very important. And you see the density of a cluster, electron density at the center of a cluster is 10 to the power minus 3. And if you go outward, the density goes down, and its X-ray luminosity reaches up to 10 to the power 45 Earths per second or so. And it's like very massive systems. And these clusters are formed through the like accretion process. So in early study of galaxy clusters, uh, or groups. In a surface brightness map, some galaxy clusters shows the centrally bright peak, and that is called as a cool core cluster, and some don't show the centrally bright peak, we call as a non-cool core clusters. And if you look the temperature profile, it's of the two systems, cool core and non-cool cool core, it's completely opposite. Cool core has a centrally low temperature. If you go outward, the temperature goes on increasing, whereas in a non-cool core cluster, it is completely opposite. So if you look the X-ray images of any group or clusters, at center you see the bright X-ray emission where the density is high, that's the relative density is high compared to the outer part. And if that is a bright source at the center, it means that the cluster or group is rapidly emitting X-ray and rapidly cooling it down due to the radiative losses. In the central gas, therefore, the central part of the cluster or group, it will lose the pressure and do not support. So the outer part of the gas is flow towards the central part that we call as a cooling flow. And this cooling flow is like most of the clusters, groups, and even large elliptical isolated galaxy we can see seen so far. So the one problem associated with this study is that due to the intense X-ray radiation, gas must cool down a long time ago compared to the Hubble cooling time. So that it predicted like 100 to 1,000 solar mass per year of a mass deposition rate we expect at the core of the central dominated galaxy, but observationally very less star formation is found at the center. And so there is a problem rises that where this cool gas goes, this sets the problem, this sets the cooling flow problem. So if you see the mass deposition rate and below the like 0.5 kilo electron volt, the mass deposition rate is very, very low. And if you see the X-ray spectrum through the high resolution X-ray spectrum from like XMM, you will see uh, you will see there is no any emission lines, but we expect from the classical cooling flow model that we expect uh, many emissions lines to contribute the cooling effect, but we don't see such a large emission lines. So the problem is like where this cool gas goes now. So this is the main problem. But if you see the LXKT relation, is a LXKT relations derived for like groups and clusters. And if you the theoretical prediction of like that X-ray luminosity is proportional to the square of the temperature of the system, but observationally from you et al. They found this LXKT relation temperature proportional to the cube of the temperature. So this is that where the extra heating comes from. If you could address this issue, then we can possibly solve the cooling flow problem. So there are many possible models or scenarios are proposed to understand this cooling flow model. That is cosmic ray heating, one of the thing, and there is another is like a thermal conduction of heat from the outer part of the clusters to the inner part. And there is also possibility of at the core this is a hiding a cool gas by some absorbing material. And there is also the mixing process is going on at the core. It will mix with the cool gas with the hotter gas, and the temperature is may increase. So there is also possibility of subcluster merging scenario. But the more convincing results we obtained so far is like a mechanical heating by the central AGN jets with the ICM. So that usually we call it as a feedback. And the feedback has like two modes depending upon its accretion. So one is like a radiative mode feedback, and it is more operative at like a high redshift systems. It's more effective at a redshift of 2 or beyond. And at this mode, the accretion, black hole accretion at a high Eddington limit, we see that, and this emit is an enormous amount of radiation. That is this AGN feedback is very radiatively efficient one. So it will gives the in the form of feedback. It will gives the galactic wind and outflows, and but it's very hard to separate from the star formation wind in this scenario. So this radiative mode, we see the some portion of objects is like radiolite, that is high excitation radio galaxies, and some small fractions. They also produce the powerful radio jets. Very small fraction, less than 10% of like in quasar kind of thing. So depending upon the weaving angle, you can also see the what type 1 and type 2 agent depending upon the weaving angle. Okay, so there is another mode is like jet mode feedback. In jet mode feedback is also with a like, different name like radio mode feedback, kinetic mode, mechanical mode, thermal mode, or maintenance mode feedback. So in this scenario, the flow accretion rate at a low Eddington limit, and this accretion is created using the ADF flow, that is a advocation dominated accretion flow. And this radiation is radiatively inefficient, and this will see in a, like a present epoch at for redshifts, and it will like FR1 type of galaxies and low excitation radio galaxies, and it produces like powerful radio jets. So here are some examples of agent feedback in radio mode with observations from the Chandra, and other wavelengths. So in the left panel image, you see this blue is like a X-ray emission, and green is like a radio emission. And you see that this radio jets is inflated, and it displaces the X-ray plasma, by using the radio plasma. So it will create like a deficiency or decrement in that region, and that we call it as a cavity. It's called as a cavity, And this is just the outcome of the central radio AGN or central radio jets. And this image will clearly shows the association between the whatever the cavity seen using the Chandra X-ray telescopes with the scene in radio. So there is like various types of X-ray cavities and bubbles. So far about 200 systems with the X-ray cavity identified, and that most of the fraction is of groups, clusters and groups, and very little or little AGN feedback is studied in individual elliptical galaxies. There are some zoo of this cavity systems, these well-known cavity systems. Like one is a like MS-075, then Hercules, Cygnus, and some groups like 5813. So in 5813, we will see like multiple pairs of cavities, like two pairs, inner pair of cavities, middle pair of cavities, and outer pair of cavities, and in a collinear form. But in other clusters, it will give the two pairs of cavities orthogonal to each other, and some groups like NGC 4636, it shows the bubbles here. You can see my cursor bubble. Here is a bubble, and with some filaments or spiral kind of a structure. Also, there is a small X-ray binary sources, large population of X-ray binary sources. And if another famous group like NGC 5044, you can see also the multiple cavities there. So, and also one cavity which shows like asymmetric cavity formation, like here A, B, C, D is like cavities, and this is the influenced, the ASM weather is influenced by like sloshing and merging, and because of that, this asymmetric cavity formation occur. So some at the low frequencies, we like see that this completely radio filled X-ray cavities. These are some few classical examples of that, which clearly shows this radio jet is forming X-ray cavities. Yeah, then we can see that the possible origin of like multiple X-ray cavities. The origin is associated with the like AGN life cycle. AGN or radio AGN life cycle. Like you know that agents are like uh, it shows the reoccurring activity. Sometimes they is on and sometimes they off. Because of that, this for each outburst or each outburst, one pair of X-ray cavities is formed, so that we get like multiple X-ray cavities, just like we see in a radio, the double radio galaxies kind of thing. This is like a recurring jet activity. Because of that, we see the multiple X-ray cavities. And if you see the like this system, orthogonal cavities, in this way, this is the possibility of jet angular reorientation is one of the things. So we can correlate that multiple pair of cavities associated with the multiple AGN outburst. And this is a mechanical one, so we can calculate the total enthalpy is like 4 times the pressure into volume. And if we can measure the volume from using the volume of X-ray cavities from seeing the X-ray images. And you can, if you know the distance from the center of a cavity, you can easily find out the time. And these cavities are moved in the ICM or IGM in like a buoyantly way with the speed of a sound. And this particular cavity is also helpful to study the AGN duty cycle of radio agents. So one thing is like do in multiple cavity system, do some smaller or larger bubble travel faster. Like in the case of a Hydra, we see the 3 pairs of cavities, inner pair AB, outer pair CD, and more outer pair EF. You can see the outer pair E is like the size is more compared to the just previous cavity. It indicates that the size is quite large, and you can see that the larger than the smaller area. In fact, outer bubble can even larger than the adiabatic expansion theory of a bubble. So possibly that larger outer bubble formed due to the merging of individual bubble that is created by the previous AGN outbursts. So using this terminal velocity, we can clearly say that this larger bubble will travel faster compared to the smaller bubble. So another concept or another point associated with the bubble or a cavity is the upliftment of cold gas from the core, and you can see that this the temperature and the metallicity map of a cluster. So we can see you can see that there is a clear separation of a metallicity distribution along the jet and non-jet directions. On jet direction, we get much more metallicity compared to the non-jet directions, and because of the cooling flow, it is a cool core cluster. Therefore, the central temperature is less. So this bubble is also responsible for uplifting the cool gas from the center to the outward. And the problem is why we care about this mechanical feedback. So we can see the very rich observation of the Perseus cluster. It shows the very enormous amount of morphological features in that, and that is very complex, and it's very difficult to understand all the processes going on there. So it's like rich. So it will show the center is a nuclear point source. It's AGN, some black region are a cavity, like ripples, sound waves, gas sloshing, and filamentary structures, large-scale asymmetries. It's tremendous features present in the system, and therefore it is very important to study the mechanical feedback. And also, this is another rich cluster, ABEL 2052. It will also show the complicated morphological features inside and outside of the cluster core. So this is the one of the motivations to study the feedback. So another is aware that this mechanical feedbacks put a very real impact in galaxy formation in evolution theory. With the famous this plot, we can clearly see that without the agent feedback and with the agent feedback, there is without agent feedback there is a over prediction of a massive galaxies in the universe. And those blue points are like the observational data points that will well match it with the simulations with the agent feedback. Therefore, it's a very clear importance of the feedback. So another thing is associated with the cooling time profiles. So the cooling is also very important in clusters. In classically, we can calculate that cooling radius is like radius at which the cooling time is less than the 7.7 gigayear. And here we see that the cluster with the central cooling time less than 1 gigayear, it contains the cavities within 10 to 20 kpc from the centers. So the longer cooling time, we don't see any X-ray cavities so far. Yeah. So another excessive brightness features seen in a Chandra images, there's cold front, and cold front are a surface brightness discontinuities associated with the temperature jumps, and it is found in very relaxed and also the dynamically merging galaxy clusters. So here we see the complete cold front, classical cold front examples that we can see the ages. And this study is very important because this cold front or shock front, it will give the very importance to understand the internal dynamics of the cluster, interdynamics of the cluster. So this cold fronts nowadays we can see in a very more galaxy groups and clusters. It's half of the galaxy clusters are with the cold front, and can be found in a 400 kpc from the center. It shows the arc, the morphology is kind of an arc shape, and even in a single system we can observe the multiple cold fronts. And the origin of this possibly is due to the gas sloshing induced by the minor mergers or off-axis merger in a cool core systems. Here one point that it's observed in both clusters, but we will focus on the cold fronts in a cool core systems. And if you check the beneath of the cold front, the gas is very denser, low entropy, and high metallicity than the plasma just above it. So thermodynamics, it indicates that this we model the cold front using the broken power law, and we can find out the age of the cold front, and we can see that the age there is a temperature jump here in a like projected and deprojected spectroscopy, and it's like and we can see that there is a pressure, constant pressure. It indicates that this cold front motion is very negligible in the intercluster medium at IGM. This is broken power law model. Okay. Yeah. Sorry. So one thing is like recently found this relation between cold front, mini halo, and a gas sloshing. So it's like currently ongoing concept here that in mini halo we can see at the edge of mini halo we see the cold front, and the caches found that cold front are strongly magnetized beneath and surrounding them. This implies the coincidence between the cold front and the edges of a mini halo. The physics is very complicated, so for the emission mechanism of like formation mechanism of cold front and formation mechanism of mini halo is it's because of the turbulence and sloshing it's occurred in the intercluster medium. If you see the shock gives like a shock, and we see the shock because of the cavities, not from the merging. So this cavity put a pressure on the surrounding ICM, and it will form the shock kind of thing. So particularly this system, it has like a circular shock around the system, and this shock is very associated with actually temperature drop in all four directions, and also shows the discontinuity in the electron density as well as the pressure profiles. So one is like a famous plot on like AGN feedback study is like a heating versus cooling. So this heating versus cooling, it shows that the mechanical energy is required to inflate the bubble is like balanced with the radiative loss, or it's balanced with the runaway cooling. And we see that the one-to-one correspondence lines between 1 PV and 16 PV, we see those more objects. So it indicates that the upper side objects here are just mostly the clusters, and the clusters in this way, and this bubbling is occurring in that cluster. It is in a continuous process of an age and outburst because it smoothly fill up that correlation. Yeah, even though there is a large uncertainties, it's because of the cavities sizes are measured by visually. And if you see at the lower systems by studied by Nielsen, it's basically the groups, and the groups is like somewhat shows the above 1 PV line. It indicates that this tension or the scatter is indicate that this bubbling scenario or the bubble formation scenario in a groups is not a continuous process in that system, rather that it is an intermediate age and outburst. Therefore, in this way, in this groups, we'll see the more cavities, and more cavity means like more cavity power. Therefore, they shifted from above the 1 PV line. 1 PV line. Then another thing is like recently, so that's like motivated size of a cooling radius over the classical, that is the quenched cooling flow radius and cool condensation radius. So Wang et al. Shows that this quenched cooling flow radius is like a very physically motivated size of a cooling radius over the classical. So both, if you consider the estimated the luminosity, cooling luminosity within these three regions, it also sufficient to balance this radiative losses, or sufficient to balance the offset, sufficiently balance the cooling. So one problem is associated with that is like why the ellipticals, individual ellipticals not studied, so very less studied for the AGN feedback, is because the Chandra's effective area at a low redshift is drastically go down from the launch. We can see at a low redshift, and because of that less effective area, it's difficult to study the individual elliptical galaxies. So this is because individual galaxies, so the next generation telescopes like AXIS will be very useful to study the AGN feedback as individual elliptical galaxies. And this is probably like not possible from the Chandra because of the effective area is less at the low energies. So another correlation is that radio jet and cavity power relations. It indicates that it shows also the scatter of order of 10 to the power 4 order of magnitudes, or even sometimes 5 order of magnitude. So this power of a cavity is like a, is or the radio source is like a is sufficiently enough to create a bubble, and that offsets the cooling. And the one thing is that the radioluminosity cannot be the large scatter, because the radioluminosity cannot be reliable gauge for the total mechanical power of the outburst, because the radio sources are poor fed with the time, and food with that, and it is shows the recurrent AGN radio activity. And because of this, and one of the reason is that because of sometimes dense environment, uh, even though the radio agent is sufficient to power, but because of the dense environment, it's not able to put cavities in a proper place. It could be another reason. So if you see this heating, you see the cavity systems or feedback study at the distant cluster. We can see that there is we evolve the cavity parameters like cavity parameters like power, enthalpy, luminosity, average radius of a cavity, and average distance of a cavity. Then we don't find any uh, significant evolutions up to the redshift of 0.5. Our sample is between like sample of Rafferty and sample of Halpha. So this there is up to now this there is no significance evaluation, because Chandra is not like a suitable instrument to look this cavity system with like a higher redshift. But so far up to this radio mode is apparently operating up to the redshift of like a 1.2. It means that we can see the bubble at 1.2 redshift. But beyond that, it's very difficult to study, not difficult to study from the Chandra. So we need to rely on the other like radio, like using a LOFAR or so they can probe up to the redshift of beyond 2 to 5, less than 5. So, and another issue that radiation is like weakly coupled at a high redshift. The radiation is very weakly coupled with the X-ray gas, which is emitting in kilo electron volt, and so therefore there is no see any atmospheric heating there. Another is important aspect is like central entropy, and this central entropy is like is a threshold of like a 30. If the central entropy is less than 30, it means that it's a cool core clusters, and after that it is a non-cool cool core systems. So this plot is to show that, so even if it is a very powerful agent outburst or very big X-ray cavities, but it fails to transfer their host from like cool core to the non-cool core cluster. It is not able to transfer. This powerful agent outburst even cannot transfer from cool core to the non-cool core cluster. The next is like multi-phase association with X-ray cavity. So like this uh, X-ray cavities. So like in group NGC 5044, it shows the very cold H-alpha filament, of temperature 10 to the power 4 Kelvin. Then in this day, and they put also the cavity locations over this plot and over this image, and they said that this H-alpha emission beneath the H-alpha emission is beneath or around the cavity. It indicates that this AGN feedback, or like the bubbles or cavities, are forming the filaments by uplifting the gas from the core, from the goals. And this is studied, this kind of study, this kind of feature is visible in many groups and clusters with such a filamentary structures. So to understand this multi-phase scenario, there is very important criteria associated with the multi-phase, that is like a ratio of a cooling time versus a ratio of cooling time to the uh, gravitationally free fall time. So this ratio suggests that if the ratios below the 30, it indicates that this cold multiphase gas condenses at the core from the warm gas, and that cold mode accretion occurred, and that cold gas accretion occurred, and that's overcome this bondy or hot accretion scenario. So if in like jet mode, the feedback maintained, actually in a jet mode feedback, the maintenance between there is a thermal balance of power of a cavity, thermal balance, and it is shown by the P cavity versus L cool plot, and it becomes prone that to local thermal instability when this ratio reaches below 30. At this point, cold dense gas starts to condense and fall towards the cluster center and accreted onto the supermassive black hole, and that supermassive black hole, and that starts the chaotic cold accretion mode. And this thing is also observed in the observations. If you look the left plot, in the left plot you can see the central entropy. There is a clear dichotomy that those objects which are emitting the H alpha emissions are placed below the 30 kilo electron volt, and those are don't emit H alpha. The entropy put in a above the 30. So this indicates that this criteria is very this is important to just detect the multiphase gas in the systems. This is the summary of my talk. So here is a X-ray cavities, shocks, and cold fronts. Edges are direct evidence of radio mode feedback, and it's allow us to measure the energy budget of cavity and radio properties. And cavities are detecting bright nearby systems so far, so it's a need to study very detailed in like a high redshift using the other radio telescope like LOFAR, or even possible than MIRCAT. And we see up to now there is no any redshift evolution, cavity parameter evolution up to the redshift of 1.3. And this cold front is the origin of that is mainly because of the off-axis minor merger present in the environment. Also, I would like to thank I will to show that the things we do not understand in this cavity physics is that how does this time scale of jet activity depends upon the host galaxy and the environment is still debatable. And one thing is that how the jet plasma interact with the surrounding medium, and how this bubble or cavity dissipate energy into the heat, and this how this bubbles cavities evolve across at all time scale with including the magnetic field and viscosity. And so, and also it's very important to study this feedback scenario at individual elliptical galaxies that was not possible from like Chandra. Thank you.
Okay, thank you so much. That's really a great talk.
Thank you.
So we have time for questions. Anyone has any question, you can raise your hand.
Sorry, I don't know where to raise a hand. If I can maybe just come in.
Yes, sure. Go ahead.
Yeah. Okay. Just something I didn't understand is this relationship you mentioned fairly early in your talk with. You said the one mechanism is more common at redshifts of 2 to 3, and also now you talk about something's up to a certain redshift. Is it not just a selection effect? I mean, I wouldn't otherwise understand why something should be more common at a certain redshift. Are you not just picking up more at those redshifts because of luminosity effects? So effectively a selection effect.
Yeah. You were asking about this like a cavity detection at a low redshift, or in this plot, right?
No. If you go right back, you said that you introduced those two mechanisms, and you said that the one is the most common at galaxies between or clusters between two and redshifts of 2 and 3. Surely, isn't that just a selection effect? Otherwise, why would something be more common at a certain distance rather than elsewhere?
Yes.
I think it probably was at the beginning of your talk when
yes,
you
right.
were.
It's about slide number 6 or so, somewhere around there.
Yeah.
I think when you were introducing the different modes.
Yes.
Yeah. This one, right?
Yes. I think if you go back one or two more.
Yes, it's about selection effect. But so far, the cavity sample is like a mixture of all, like groups, clusters, and ellipticals one. So, and it's like, so it's a not like a particular one, because it's a mixed sample actually.
Yeah, I don't know if we're understanding each other, but also later on you said you haven't found any evidence of something up to the redshift of z is equal to 1.3. But sure, aren't you just saying that you expect it to go beyond that as well? It's just that you haven't had the chance to test it there, but you would still expect it to happen there. It's just it becomes ever more difficult to do those measurements because these galaxies are further away.
Yeah, that there is a problem like redshift dimming effect is also there. Also, this radiation like weakly coupled to the like hot gas. So to study this beyond this, we need like a good spatial resolution as well. So this is like
but would you
more
expect it
technical
to
limitations.
change if you go to a higher redshift?
Yeah.
Why?
The X-ray emitting gas, we see this bubble with X-ray emitting gas, and it is very weakly coupled with this high redshift gas, and the density is also low at early stage of a cluster formation. Therefore, we get like less X-ray emissions from there.
Okay.
Yeah.
All right.
Yeah,
Thanks.
the density is low at early stage formation, so there is a less X-ray emission we expect.
I see. Okay.
As we go, as you go to high redshift.
Okay.
Yeah. Thanks.
Okay, any more questions? I just wanted to ask, I think in one of your slides you mentioned that the radioluminosity is not reliable to determine the mechanical power of the jet.
Yeah.
Can you just explain a bit more about that?
Yeah. This one, right? Yeah.
I think so.
So, yeah, this one. Actually, if you see this ratio of these two estimate, so we'll see this ratio is very large scatter, and because of large scatter, we get not tight correlations, and also there is like cavity measure is done by visually, so there is also prone to the systematic errors. Because of that, the scatter is quite high, and also that's the radio like with the weak radio power, but some system shows very powerful radio jets or lobes. Radio jets or lobes. So maybe this system, if the power with the low radio power, if it able to be and this low power is because what happens, this is the agent, radio agent shows like a recurring object, means sometimes it is just switch on and sometimes switch off the radiations, and because of that this like the total measurement from using the radio is not like a reliable one, and it's like a fade with the time also.
So you mean that the cavity power is more reliable?
Yes. So yeah, the cavity power we can see directly from the, we can estimate from the directly from the image, but still there is a projection effect. But yeah,
Okay, thanks.
yeah. Mm.
Okay, so if there's not any more questions, we can end the meeting now. Thanks again, Satish. It was
Thank you.
really nice. Thank you, everyone, and we'll see you in the next colloquium.
Okay, thank you. Yeah.